In the last video, I've talked about how de Broglie imagined that an electron could behave like a wave and proposed a formula for the wavelength of an electron that has a momentum p, if it can behave like a wave. So in this video, I'm talking about I will try to talk about how we can make an experiment to actually check this out. So first, we have to find a diffraction grating or double slit. Now, you know, if you want to do a successful interference experiment, say for light, the important thing is to choose slits that have the correct spacing. The spacing should be a few times of the wavelength of the light wave, so that we can observe the fringes clearly. If not, the fringes would either be too close together or too far apart, and you can't really see anything. So that's the first thing that we need to do. We need to work out what might be the wavelength of a beam of electron that we can use. So let's do that. Let's work that out. Let's work something out. And okay, let me write down the equation for the diffraction grating. Let's say that angle is theta and the spacing between the slits is d, and let's say the wavelength is lambda, and the order of the wavelength would be we call n, so that's the zero order fringe, first order fringe, then there, and so on. So I'm just going to write down what we have learned from diffraction grating many videos ago, that d sine theta is equal to a whole number, or the order of the fringe, times the wavelength. So this formula allows us to actually, if we know lambda, to work out what theta we might expect, or what d we might want to use. Okay, so how do we go about finding the wavelength of an electron? So let's say that's an electron, and let's say it travels at a certain velocity v, and it has a certain mass m. It has the mass me, and we know that the charge is e. Okay. Now we need to think about this. We need to think about how we would normally make a beam of electron or accelerate electron. We would accelerate it using a voltage. The kind of typical voltage that is available, well, we can have a wide range from a few volts to a few thousand volts or more. So I'm just going to take as an example, I'm going to take a voltage of maybe 50 volts. So I'm going to say, right, let's say the energy, the kinetic energy of this electron is 50 eV. Let's say that's the kinetic energy. Okay, that's my half mv squared. That's me. So it means that if I have, suppose that I have a 50 eV energy of electron, or I have a beam of electron, in which each electron is 50 eV. That means that it must have been accelerated by a voltage of 50 volts before that. So, okay, now this means that I can calculate the momentum. Okay, remember that we need to know the momentum to find the wavelength. Let me write down the Broglie's relation again. Okay, that's the formula to find the wavelength from the momentum. So it would be more convenient if I write this as p squared over 2me. Right, so that's just another way of writing half of mv squared. And this would be equal to E being the 50 eV. So let's try and find the wavelength now. If I rearrange this, I get P equals to square root of 2me times E. Okay, and we can find this. We can find P because we know ME. ME is 9.1 times 10 to the power minus 31 kilograms, and E is 50 eV. Now 50 eV has to be converted to joules, so that will be 50 times E, which is the charge of an electron, 1.6 times 10 to the minus 19. So that's the mass in kg, that's the kinetic energy in joules. So we can use our calculator to find this. Alright, and after using our calculator to find this, we can substitute it into here. Okay, and H, we know H is let's say 6.63 times 10 to the minus 34 joule second. Okay, so we have all the numbers we need, and therefore we can find the answer. And if you use your calculator, you'll find that the answer is 1.734 angstrom. That is a very, very small wavelength. Now, if you think about it, light, you might already have some idea that the wavelength of light is just under a micrometer. It's a few hundred nanometers. Okay, so it's just under a micrometer. But we're talking about angstrom here. Right? Angstrom is 10 to the power minus 10 meter. So this is much, much shorter than the speed of light. Now to see how big this is, an atom is about the size of an atom. This is actually about the size of an atom, which is maybe about 1 angstrom or so. Now that immediately means that there is a problem. Okay, it is a problem because how can we make slits that are 1 or 2 atoms apart? If we just take a knife and cut a slit in a piece of paper, that must be many atoms wide. Right, that must be many atoms wide. So it is basically quite impossible for us to actually cut slits that have this kind of spacing in a piece of object. But there is another way out. There is another way out. Let's get this out. Okay, so let me write out the result that I've calculated. For E equals to 50 eV, for 50 eV electron, the predicted wavelength from the Broglie's relation is 1.734 angstrom. Now, I mean, if we are ever going to do an experiment with this to try and observe any interference pattern, we need a grating with slit spacings that are a few atoms wide. So there is a way. Turns out that there is a way. In 1927, just about 3 years after de Broglie proposed this idea that electron might be a wave, two persons, Davison and Germer, they were able to design an experiment. But what grating did they use? They actually use a nickel crystal. Right? Nickel is a kind of metal, but they did not actually try to cut any slits into the crystal. What they did was they used the atoms in the crystal. They used the atoms in the crystal as the slits, because the atom itself would be maybe about an angstrom or two distance. Right? Typically, in a metal crystal, the spacing between atoms might be, say, about 3 angstrom, for example. So in a nickel crystal, for example, there would be lots and lots of atoms arranged in a regular array. In a crystal is usually a solid with atoms arranged in a regular pattern. So they would almost always have regular spacing, equal spacing apart. They would have equal spacings between the atoms. Now, how can this be used as a diffraction grating? Well, suppose that we shoot a beam of electrons at this, and suppose that the beam of electron is a wave. So we shoot this electron, lots of electrons perhaps, at the surface. Now, when this wave of electrons hit the surface, you can imagine that each atom is, if you imagine that the wave of electrons is like ripples on the surface of water, you might imagine that each atom is like a rock. It's like a rock in the water. So when the ripple hits the rock, it bounces off, it gets reflected and produces another ripple. So when this electron wave hits each atom, it would bounce off with these ripples. I mean, assuming that the electron is actually a wave. Okay. So that ripples bouncing off each atom. Now, if you compare this with what I've drawn earlier for a wave going through the slits of a diffraction grating, you see that the ripples here and the ripples there looks pretty much the same. Okay, and it's this brilliant idea that allowed Davison and Germer to carry out this experiment. Now, and if indeed the electrons are waves, then what we would expect to see is that these ripples would interfere and give maybe a fringe in this direction, a fringe in that direction, a fringe in that direction, as we would expect from the diffraction grating, right, at some angle apart, theta, and it gives nothing in between. Now, that's not what we would expect if electrons are particles. If electrons are particles, you might imagine lots of little ball bearings or lots of little bits of sand hitting the atoms, and they will just bounce off at random, right, all over the place. You're not going to get fringes and destructive interference. So Davidson and Germer carried out these experiments with their, maybe around 50 eV beam of electrons, and what they observed was actually fringes, right? Indeed, if they have used 50 eV, I think they used maybe 40 or 60 or some other values, but let's say they used 50 eV, then they would have observed a fringe at an angle of 35.32 degrees. And they observed a fringe here, here, and here, and in between there was nothing. There's no electron coming out in between. So these are very clear fringe patterns that Davidson and Germer observed. And this 35.32 degrees is exactly what will be predicted by this equation when n here is equal to 1. And when you put in the lambda from there into this equation, and you put in the 3 angstrom into the d, you can calculate theta. You can try that out on your calculator now, and you'll find that this is the actual value. Okay, so Davidson and Germer did the experiment and they observed the angle of the fringes. They observed fringes, of course, which already showed that it's a wave, and they observed it in the angle given by this formula using the wavelength that was predicted by the Broglie. And that is a success on both fronts. A success in demonstrating that electrons are indeed waves, and also a success in showing that the Broglie's relation, that's this one, that lambda is equal to h over p, h over the momentum, that it is actually correct. So in one experiment, Davidson and Germer demonstrated the wave nature of particles and the Broglie's relation.